Very much for introduction. Good morning. My name is Bong Jae Lee. I'm from KAIST, South Korea. And first of all, I thank Mauro for inviting me to this conference. And it is my great pleasure to introduce my work in this community. And in the morning, we talk a lot about the Casimir force, and let me change the focus to the energy transfer around across the small vacuum gap. And I'll introduce what I have been working on past 10 years in South Korea. For the near field thermal radiation, when the gap between the two parallel surfaces get closer than the characteristic wavelengths of thermal radiation, then the radiative heat transfer start to show gap dependence, and that is due to the photon tunneling of the evanescent wave, and that will enhance the heat transfer exceed the black body radiation limit governed in the far field limit. So we're trying to utilize the enhanced near field heat transfer in the very small vacuum gap distances between two surfaces and utilize it for energy conversion devices. And this is very brief introduction of the near field thermal radiations. So for my group, we are working on how we can utilize such near field phenomena and exploit it and to enhance the performance of the near field thermal photovoltaic devices. So we have a thermal emitter and a TPV cell, and if we maintain the vacuum gap distances, the emitter and the cell very small, then we can utilize the near field enhancement that will eventually provide us enhance the power throughput of these devices, and hopefully we may enhance the efficiency, and I'll address that later. So to realize the near field TPV devices, and we need at least the three requirements, and the emitter temperature should be as high as possible. That is obvious due to the second law of the thermodynamics, and to utilize the near field effect, the gap distance be as small as possible, and to have a meaningful power out of this device, the surface area is as wide as possible. And these two are the competing factors to realize the devices. Also, maintaining the high temperature difference between the emitter and the receiver is also very challenging. So long journey to the near field thermal radiation in my group start from about 10 years ago, and when I moved to the KAIST, and we, as a mechanical engineer, I first employed the MEMS, the based platform for the measurements. So this is the cross-section of our first generation of the device. The heat transfer area is here, and we made a trench and make the firm contact besides the trench so that the conduction and the radiation we separate from the design. And the width of this heat transfer area is about 500 micron. The gap distance is about 500 nanometer. So the aspect ratio is 1 to 1000. And to the depth directions, we have about 1.3 centimeter. So we have essentially, it's a very long line. And we have a emitter part, top side. And the back side, we have a heater to increase the temperature of the emitter, and the receiver part, and these are the spacers, this part, and to maintain the gap. And the first generation of our device has a clear limitation that there is no means to control the gap distance between these two heat transfer areas made of doped silicons. We can vary the gap distance, but we cannot control in precise manner. But with this very primitive design, we performed the experiments, and we got the heat transfer, radiative heat transfer with respect to the vacuum gap. And we demonstrate that we can exceed the black body limit and in very small distances. And the limit we achieved is about 400 nanometers with this very simple design of the MEMS platform. From that, and we identify the challenges. And from the theory tells us that the near field enhancement becomes greater at very small distances. And this is 1 micrometer, and this is 200 nanometers. Well, and what we achieve is about here, 400 nanometers. So if we decrease the gap distance further and maintaining at the same time the wide surface area that is desirable, but from our devices, we could not achieve that. So I know there are many people, and they take the approaches that using the precise the actuators to nano actuator to maintain the like a 10 nanometer scale, so 100 nanometer scale, the gap distance. It was possible, but we think of the devices, and we did not want compromise the surface area, so we take the alternative route. So for instance, we can modify surface conditions using optical metamaterial, basically sub-wavelength sized the nanostructures. We all know that it can change, it can interact with the radiation, and it can change the radiative property in the far field. In the near field, we can take the similar analogies, so that the sub-wavelength structure may change the near field heat transfer rate without changing given the vacuum gap. So in other words, what we're trying to achieve is that if this is the original near field heat transfer curves, heat transfer rate versus the vacuum gap, if we somehow change the surface conditions and shift these curves to the right, then to achieve the same level of heat transfer, we can gain the vacuum gap about 300 nanometers. Yeah, it sounds not much, but for our devices, it means a lot. Okay? So how we do that? So we think back to the basic the theories, and we know that since the near field radiation involves tunneling of evanescent waves, and if the materials support the electric resonances like a surface plasmon or surface phonopolaritones, the evanescent wave associated with such resonances will be greatly amplified, and the near field heat transfer are dominated by such mode. So this is a very simple example of near field heat transfer rate between two doped silicon plates, and by changing the doping concentrations, and we can change the heat transfer, near field heat transfer rate curves. And that means that by changing the doping concentrations, we can change the resonance condition of surface plasmon. And by changing the surface plasmon dispersion curves, and there are means to control the near field radiations in a way that we can gain the gap distances, okay, to achieve the same level of the heat transfer. So that was our intentions. So first we look into the very simple geometry using the 2D materials like a graphene. So initially we have doped silicons, because we have the doped silicon calculation already. So we start with the doped silicon, same configurations, and we apply the monolayer graphene on the surface and how it can change. And this is the no graphenes, so bare doped silicon plates. And obviously you can see that at the same vacuum gap, with the use of the graphene, we can increase the heat transfer rate. Also, at the same level of the heat transfer rate, and we can gain the vacuum gap distances using the graphene. So the idea works, and that is related to, fundamentals are related to the coupling of the surface plasmon in the doped silicon, as well as the surface plasmon supported by the graphene. So we apply these ideas to the TPP devices. So doped silicon, we take the source, and we use indium antimonide TPP cell, and use a monolayer graphene on the TPP side, and hope that the graphene can enhance the heat transfer rate as well as the power throughput of the devices. And the basic idea works by matching the resonance frequencies of doped silicon and the graphene plasmons. But unfortunately, we found that the effect of graphene in these asymmetric configurations, emitter and the cell, different material, but previously we consider symmetric configurations, same emitter and the receiver. So for the device, the effect of graphene quickly disappear less than 100 nanometer vacuum gaps. So it couldn't work for our devices because the minimum gap we achieved is around 400 nanometer at the time. So we think about, so why? And it becomes very obvious now. So if you think about the tunneling configurations, and we take the parallel component of the wave vector in vacuum as a beta. Evanescent wave has a high parallel wave component so that it has a large magnitude of the imaginary component, imaginary normal wave vector component. So if the beta is a very large, much larger than the wave vector in the vacuum, then the normal wave vector component in vacuum approximate as I beta simply. And if we see the amplitude of the evanescent waves, and it decays like an exponential minus beta, and the g is the direction from the surfaces, distance from the surfaces. So larger beta rarely contributes to the heat transfer when the vacuum gap width become larger, because these evanescent wave with a high magnitude of wave, parallel component of wave vector quickly decays and could not reach the other surfaces. So it rarely contributes to the tunneling. If we have a small gap, it's okay, but the larger gap, we cannot. So the gap distance between the two surfaces is actually like like a bandpass filter for the evanescent wave with a parallel wave vector component. So if we want to control the SPP dispersion, it is desirable to shift SPP dispersion to close to the vacuum gap line, a vacuum light line, so that beta becomes close to this magnitude of the wave vector in the vacuum. And previously, what we deal with is that the normalized beta is about 50 times or 100 times of the magnitude of the vacuum, wave vector. So it quickly decays. So larger vacuum gap, it cannot contribute. So beta was too high. So how can we shift the resonance mode to closer to the vacuum gap line, vacuum light line? And we consider, instead of the single layer, we consider multi-layers, because multi-layers support multiple plasmons, and they can couple together, and by coupling, their dispersions spread out, and some of them shift to the larger beta region, some of them shift to the low beta region, and we are utilizing the dispersion curves shift to the low beta region. So we consider metallodielectric multilayers, and you can also consider it as a hyperbolic metamaterials, and each metal dielectric surfaces, and we can have plasmons, and since the metal thickness are very thin, so that all the modes are coupled together, and some of the modes appears in the beta range, it's much smaller. So we are on the order of less than 10. Previously, the beta value order of 50 to 100 times of the magnitude of vacuum gap. So from this calculation, we can see that the enhancement exists even in very long distances due to interference effect as well as the coupling of the plasmonic resonances. So from the calculations, we look back our earlier designs of the same TPB systems. And instead of using the monolayer graphene, we use a multi-layer graphene, so to introduce many interfaces for occurring the coupled plasmons. And the idea works idea works to some extent. So initially, monolayer graphene enhanced the power output to about 50 nanometers, but we can extend it to around 100 nanometers. So basically, idea works. So from the calculations and the theory actually confirmed that by coupling of these multiple resonances, and we do shift the beta to the smaller values, and that allow us tunneling of avalanche wave with the smaller value of the beta. So from there, we do experiments. So we fabricate metallodielectric multilayers in titanium as a metal. We choose MgF2 as a dielectric, and the MgF2 has a strong phonon absorption band in its support surface phonopolaritones, and it is well known that MgF2 has a very high near field thermal radiations. But for our design, MgF2 did not play role as an emitter. It simply acts as a dielectric spacer for these metal layers, so that it supports multiple surface plasmonic resonances. And this second version of our device, and the overall geometry was pretty much the same. The width about 500 nanometers, 500 micrometers, length, depth, directions about 1 centimeter. So this is just a simple photography we can take with our smartphone, not the microscopic image. And we employ the linear motion guide in order to control the gap distance between two surfaces. And to measure heat transfer rate, and we implement the two temperature sensors, so that by monitoring the temperature differences between 2 points, we can estimate how much heat transfer rate flows through 2 points. So this is how we do the heat flux calibrations. So we initially position this emitter in the far field regime, and we have a calibration heater underneath the receiver, and we provide the value of the Q, heat generation here, and monitoring the temperature differences at two positions. And whatever generated heat here will pass through two parts. And even though we tried our best to make these symmetric conditions, the separation of the heat transfer rate should not be the half and half. So we have unknown factor G. So G portion goes to left direction, one over G goes to right directions. So we can set up these measurement equations. So what we're trying to do is Q versus temperature difference. So if we rearrange the equations, and we can come up with this linear relationship. So to the many measurements, and we can fit with the linear functions. And this is pre-calibrations. For the measurements, and we put this emitter and the receiver in the close proximities, and without applying this calibration heaters. So whatever the heat transfer from the emitter to receiver will eventually pass through these calibration heater regions, so that the heat transfer rate QE emitter to receiver here, and generated calibration heat generations at this point, we assume that they act as the same way. That's the basic assumptions of this calibration. And for the vacuum gap distance, and we use the capacitance measurement, and to do so, we intentionally divided the receiver side as a 4 segment, so that we can sequentially monitoring the capacitance here and there, here, there, here, there, so that we can sequentially monitoring how the gap distance is changing locally, not locally, but dividing these 4 segments. So this is to maintain the parallelism. We trying to get the same similar level of the capacitance in the first one and the fourth one. So even though there are some bendings, we're trying to match the first and the fourth one. And if we have a physical contact, then we can directly monitor that event from the resistance measurement between the two segments. So from that, this is what we got, our measurement result. So as you can see, radiative heat flux versus vacuum gap. And this is a bulk line, calculated line between the two titanium surface. And this is what we got for the metallodielectric multi-layers. As you can see, for the similar level of the heat transfer rate, we are gaining the vacuum gap distances. At the same gap, we are enhancing that. And to verify what we designed is really utilizing the coupled surface plasmon in the whole layers, which I didn't mention that we fabricate the 3 period of Ti and MgF2 unit cells, so 6 layers. So if we change the number of unit cells and the 3 period and the 1 period unit cells, and we have a different heat transfer rate. That means that it is not the first layer, the Ti film, thin film effect. It is really the volumetric, the plasmonic coupling effect from the surface, from the structure. And we also changed the volumetric filling ratio. So from the effective medium theory, and we can define the volumetric filling ratio, period, and the thickness of the Ti layer. So F is equal to 0.1 and the F changes to 0.23, and it also changes. So that means that by changing the thickness of Ti and thickness of the MgF2, we change the nature of the coupling of the plasmonic resonances in multi-layer structure. After that, and we think about the asymmetric configurations. Again, this idea, we are using the same the multi-layer structures. For TPV applications, we have to consider the asymmetric configurations. Emitter and the cell, they are different. So we did a very simple experiment. So we fixed the emitter as a doped silicon, and we set the receiver as a SiO2 and SiO2 with a thin Ti film as a coupler between the plasmonic resonance in the doped silicon and the plasmonic resonance in the titanium. So using the single layer as a coupler, we're trying to enhance the heat transfer while we're trying to gaining the vacuum gap distances at the same level of the heat transfer. So we use the basically same design, and we fabricate the samples. And for here, because we have a dielectric receiver, so we put the very thin, the Ti layers, and covering about 3% of the heat transfer area as a capacitance pad. And using that, we are monitoring the capacitance just like before. And for these measurements, we also improved our measurement scheme that by removing the heat flux, by removing the temperature sensors, because the fabricating temperature sensor was okay, but temperature heat flux calibration requires the calibration heater underneath the receiver. And we had a problem with the insulating of such thin layers underneath the receiver. So what we do is that we're monitoring the heat input from the heater by changing the gap distance, the heat transfer rate to maintain the same emitter temperature should increase. So we do differential measurements. So we set as a reference point in the far field, and it consists of the two contributions, far field radiations between emitter and the receiver, and whatever the heat loss to the chambers. If we maintaining the environmental conditions, chamber temperature and others are relatively constant, we can assume that this heat loss will constant regardless of these vacuum gap distances, whether it is far field or near field. And the far field contribution is ballistic transport, so it should not depend on the vacuum gap. in the near field, we have an enhanced near field radiation effect. So we assume the constant, and we are taking this differential measurement. And we verify with our previous sample, with the temperature sensors, that we did a two measurement scheme. One was a previous measured by the sensor, and the other is monitoring the heat flux from the heater, and they pretty much agree very well. So simple measurement can be done. So using that, we did a experiment. So the both case, we have a doped silicon as an emitter, and the receiver, one is a bare silicon dioxide, the other is a bare silicon dioxide with 10 nanometer high film. And you can clearly see that high film, the sample, will have a higher heat transfer rate, also gaining couple hundreds of the vacuum gap distances for us. And we look up this enhancement mechanism. And interestingly, since we use a metallic coupler and the doped silicon, if we have a heavily doped, then doped silicon is behaved like a lossy metal. So in metal to metal, near field radiation, S polarization play a role. So we compare, we calculate the enhancement in the P and S polarizations. P polarization, due to the coupling of the plasmonic resonance, we do observe the enhancement. S polarizations, we have also enhancement due to the so-called thin film effect, basically interference effect inside very small, very thin tight film, as well as the thin tight film has a more lossy, greater loss because of the electron boundary scattering effect, and that will change the sharp, the radiation, the spectral radiation peak to be broader, so that overall heat transfer can enhance. And we calculate this plasmonic dispersion curves. So the reference samples, the resonance in doped silicon side and the resonance in the silicon dioxide side do not match in terms of the frequency. If we have a titanium as a coupler, the vacuum tie SiO2 configurations will have changed plasmonic resonances, and the doped silicon and the new tie SiO2 configurations will have some overlap. So that is the mechanism of the heat transfer enhancement. And let me skip this part. And the final part that after this of the all near field measurements, and we're trying to do the energy conversion experiment. And we decide to fabricate the Schottky junction TPB cell instead of the PN junction cell. And not because Schottky junction is better, but because our limitation in fabricating PN junction with a low band gap semiconductor, that was very difficult. So we use gallium antimonide and gold as a metallic thin films, and form the Schottky junctions, and characterize is the dark current, okay, and using the fermionic emission and the secondary, and the secondary consists of the tunneling and the SRH recombinations, and we are able to fit this IV characteristics of this our cell. And using cell, we perform the near field conversion experiment, and we changed the design because we cannot make like a line-shaped cell. So we make a small area, like a circular, the Schottky cell, so that the emitter also become the circular shape. The emitter is made of the doped silicons, and we have the capacitance head around the receiver, the 3 segments, so that we are monitoring the parallelism between 2 surfaces. And this is what it looked like. So emitter side, and there are heaters, and the heat transfer area, doped silicons, and the capacitance electrodes. And there are some the height differences, because this one we're trying try the path not to perturb the heat transfer area, so that we intentionally put some steps. And we are measuring it so that by monitoring the capacitance, we are estimating the gap distance between those two. And this is the TPV cell. Active area is about 700 micron. And to characterize, before we doing the conversion experiment, we characterized our cell. So we made the two different sizes. One is 1.6 millimeter. The other one is 0.7 millimeter. Okay. And because the commercial instrument in the Korea Institute of the Energy Research, they could not measure such small one. So we made two, and we send it to characterize the quantum efficiency. And we use a filter wheel and the solar simulator. We did our own characterization at few points, and it agree well. For the smaller devices that we use for the near field measurement, we use the verified method and characterize it. As you can see, the quantum efficiency of the larger devices and the small devices are not quite, somewhat different, and there is no reason to do so. So this is the sample-to-sample variation clearly shows our limitations, okay, in making such devices. So let me skip. One thing that we intentionally put the PV cell on the cold head connected to the refrigerator, so that we trying to do the low temperature measurements. And we first characterize in the far field the power output enhancement is about 10 times, so it's huge. But in the near field, because of the vibration of this cold head connected to the refrigerator, that prevents us to maintain the small vacuum gap. So we could not do, actually. So that was also our design limitations. And this is the result. And what we observe is that from about 2 microns down to about 300 nanometers, we observe the power output of our TPV cell shows oscillatory natures. And that is actually due to the interference effect of the propagating waves between the two surfaces. Initially, if we consider the heat transfer rate between two surfaces, because of the long wavelength contributions, and we do have the dominated evanescent, evanescent tunneling between two surfaces. But if we use a PV cell, because it has a band gap and it can only accept the photons with a higher energy than the band gap energy, so it acts like a short pass filter in terms of wavelengths. So long wavelengths evanescent tunneling contribution will disappear. That what we achieved in the vacuum gap, we can only mainly utilize the propagating waves that amplify the interference, so that we observe such oscillatory nature. So I'm a little bit off. So what we do basically, so in terms of the heat transfer, spectral heat flux, because we have about 800 Kelvin, so because of the Planck distributions, it will amplify, it will shows the large heat transfer rate in the long wavelength. But if you use the PV cell, because of the band gap, it cut off, so that Planck distribution which has a long wavelength filter, just like, and PV cell has a short wavelength filter. So if you combine those two, what we are actually doing is that it's just like measuring the spectral peak of the radiative heat transfer. That's what we ended up. Finally, I just want to introduce what we are trying to do. So we go back to the MEMS, okay? And we're trying to use a new fabrication technique. It's called the silicon on knotting. So using the high temperature diffusion process, these the filler, like a whole arrays, can be merged and can form the membrane on the cavity, just like these structures. And these are used a lot for the MEMS sensors. So we're trying to use it to maintaining the vacuum gap, nanoscale vacuum gap between the two surfaces. So we did a very primitive, the feasibility test. So we make a silicon membrane, cavity and silicons, and we oxidized it so that silicon changed to SiO2 membrane and substrate, some parts changed to SiO2. And by oxidization and the lattice expand, so that the cavity or gap distances shrinks. So we are able to achieve like around 200 nanometers without having the spacers, without having the positioner. And right now it's about 50 micron, the width, but this SON sample can be fabricated in the wafer scale. So we're trying to make this to the centimeter scale so that we can make like on-chip devices afterwards. And this work is collaboration with Professor Bong Jae Lee in our department. He's MEMS guy, so we are working on this right now. With that, for the near field energy conversion, in terms of the power output, the near field and the far field, they are competing, they are competitive. However, unfortunately, the power conversion efficiency, far field is outperformed than the near field. So there are rooms for enhancing the power conversion efficiencies in the near field devices. Otherwise, the near field TPV devices cannot compete with the far field counterpart. So this is the direction we are heading right now. With the acknowledging of my students, thank you very much for your attention.
Okay. Thank you, Bong Jae, for the talk. And we have time for a couple of questions.
Yeah, I have a question about the efficiency. You had defined the efficiency, you used the efficiency as the ratio between the heat and the work, no?
Right.
Given to the system. But this is the efficiency based on in the first law. But there is an efficiency based on the second law, which consider the dissipation more accurately, right? And then this second law efficiency is smaller. Normally, it's very smaller than the other one. Perhaps it could be interesting to see.
Right. Yeah, you're right. And everything what I present here is first law, and the best for the near field. I think the French group, they achieved like a 14%. Ours is we cannot see. I have to plot in the log scale because but we use the Schottky junction, and it has a very low efficiencies. And the far field can reach about 35 or even 40%, close to 40%, first law efficiency, right? So there are still about the double, more than double gaps, right?
More questions?
Can you go to slide 31? Just have a quick question about it. Yeah, these are experimentally measured spectrum, or they're calculated spectrum?
This is calculated. Yeah.
How does the experimental measure spectrum look like?
Actually, we cannot measure spectrum. What we only measure is
it's near field. Okay. Yeah.
Yes.
Yeah. Thanks.
Yeah.
What limits the 400 nanometer? What limit you to go to lower spacing?
Actually, the banding, I think the banding of the wafers, and we trying to have as wide surface area as possible. That's the reason why. But from this measurement, we greatly limit our surface area, like 0.5 millimeter. Still, we can achieve like 300 nanometers, not much improved. So I think, I know the Pramod, he reached a much smaller gap. So that may be related to limitation of our actuator.
Okay.
Bong Jae, can you go to slide 31 as well? So what limits you to go higher temperature beyond 800 Kelvin? So in that case, you can shift your spectrum a little bit towards near infrared.
Yes.
Right?
Yeah. Obviously, we can increase the power output. Obviously, but we at the high temperatures, our heater was not stable. So right now we are trying to use the concentrated solar system to increase the temperature of the emitter beyond this. But that was our limit, clear limit.
So your heater is an electrical heater, right?
Right.
Okay.
Yes.
Last question.
Yongji, in the last slide, you showed this comparison between far field measurements and near field, right? So all the far field work was with much higher temperature emitters, I suspect, right? That's where the efficiency, I'm not even sure if all of that is experimental work, but certainly the more recent advances at 35% to 40% are like way above, like close to 2000 Kelvin, right? And that's where I think if we do a comparison at a given temperature, right, where I don't think near field is performing much more poorly than far field, right? Yeah. So the challenge for us is to get to very high temperatures. Right.
So the temperature of the emitter, actually one point, you can, as you mentioned. Another point I mentioned is, I think is the contact, front contact. Because to maintain the small gap, the thickness of the front contact should be thin, and that will increase the resistance. So resistance loss play a very important role.
Well, the very last.
I would like to make a comment also on this curve, the same curve, because some of the people who have made this calculation do not take into account the power they use to cool down the cell. And then at the end, sometimes the efficiency becomes negative. Because here it's plotted just with respect to the emitter temperature, but the temperature of the cell is not the same in all these setups, and it's just this comment.
Right.
So probably U efficiency is better than some of this one.
Thanks for your comments. So for your information, I did not mention this red color was the calculation of the near field devices. So as you mentioned, clearly the calculation is much better than the experiments. That's why I'm saying there are some rooms for improvement.
Okay, we thank again Bong Jae.
Thank you.